Hey, welcome back to episode 3. Today, we're going to do two things that go together nicely. First, we're going to learn how to read a compact smart contract, not write one from scratch. Just open one, look at it, and understand every piece. Think of it like learning to read a recipe before you try cooking. Second, once we can read compact, we're going to let two different AI tools write it for us. Web3 Fast and Cloud Code with Ada Labs Midnight plugin and see how their output compares. Let's dive in. Four things you will walk away with today. Number one, you will know how to read compact. By the end of the next hour, words like ledger, witness, circuit, disclose, assert, they will feel like old friends. Nothing will look like magic. Number two, we will study 4 real smart contracts, pulled straight from the official Midnight documentation. We pick them carefully. Each one teaches something new on top of the last one. So by the end, you have seen every major pattern you will meet in the wild. Number three, you will be comfortable asking an AI to generate a contract for you. And more importantly, you will know how to check whether what it generates actually makes sense. And number four, you will see two AI tools compete head to head on exactly the same prompt. No tricks, no unfair advantages. So you just can pick the right one for you. Before we open a single file, I want to tell you 3 things that make Compact feel different from anything you may have used before. Solidity, move, whatever. First, privacy is the default. In most smart contract language, everything is public, unless you work hard to hide it. In Compact, it's the opposite. Every value is private unless you explicitly say publish this. And when you publish, you use a specific word for it, disclose. Remember that word. We will use it a lot. Second, dual state. A compact contract has two worlds living side by side. There's the public ledger data that lives on the Midnight blockchain that anyone can read, and there's private data that lives only on your own device. We call that a witness. The same function can touch both. Cool, right? Third, when you compile a compact contract, it doesn't just become bytecode, it becomes a zero knowledge proof. So when someone runs your contract, what gets posted to the blockchain isn't their inputs. It's a mathematical proof that they follow the rules without revealing what they did. Quick reminder, Bit9 is Cardano privacy-focused partner chain, built by IOG, the same team behind Cardano itself. Compact is its smart contract language. Here's the shape of every compact contract. I'm showing you this now because once you see it, you will recognize it in every file you ever open. At the top of the file, you have a pragma, which is just saying, hey, this file was written for compact version such and such. And import statements, just like in any other language, pulling in the standard library. Below that, 3 kinds of declaration. Ledger is your public storage. Whatever you put there goes on chain, and everyone can see it. Witness is your private storage. It lives on the user device, never touches the chain. And circuit, this is the actual function that users call. A circuit can read from witnesses, write to the ledger, and enforce rules using assert and disclose. When the compiler finishes, each circuit has become a zero knowledge proof. That's what actually hit the blockchain. The network can verify the proof is valid without ever seeing the private inputs. That's the whole magic of Midnight in one sentence. 5 moving parts total. That's it. That's the whole language. 8 words. Learn this, and you can read just about any compact contract you will ever meet. Ledger means this value lives on the blockchain. Everyone can read it. Seal. Ledger is the same, except once it's written, usually by the constructor, it's frozen, carved in stone. Think of it like setting the maximum number of guests at the party before the party starts. Nobody can change it later. Witness is the opposite of ledger. It's private value that lives on the user's device. You declare it in compact, but you actually implement it in TypeScript in your app. Circuit is a function users can call. It's what compiles to a zero-knowledge proof. Disclose is a word you use to promote something private into something public. And assert is your bouncer. If the condition isn't true, the whole transaction is rejected. Then three collection types: map, set, and counter. Exactly what they sound like. And two cryptographic tools: persistentHash for deterministic hashing and commitWithSk, a pattern for making cryptographic commitments tied to a secret key. Don't worry if that's fuzzy now. We will see them both in action. The Midnight docs publish 6 reference contracts. We pick these 4 because they build on each other perfectly. Each one adds new concepts without repeating. Calculator is our warm-up. Tiny, about 20 lines. It teaches the most single important pattern in Midnight. Do expensive work off-chain, verify it cheaply on-chain. Token transfer is second. It turns Midnight to token worlds. One where balances are public like a normal bank account, and one where there's hidden like cash in an envelope. Guest list is where it gets interesting. Access control, cryptographic commitments, per app identities. The privacy toolkit really starts to shine here. Election is our boss level. A full anonymous vote with a state machine, commit reveal, tally counters. Pretty much every compact feature in one contract. 2 we skip: private reserve auction because it overlaps heavily with guest list and election, and battleship, which is about 200 lines and mostly repeats the same patterns. Great for a future episode, too much for today. Once you can read compact, writing it by hand isn't the only option anymore. We are going to ask 2 AI tools to generate the same 4 contracts. Web3 Fast is a free website. You type, it spits out compact. 0 install, no account needed. Anyone can use it right now. Cloud Code with the Ada Labs Midnight plugin is different. It lives in your terminal. It's conversational, and the plugin gives it the Midnight specific context through 4 skills. It does require a cloud subscription. Same for prompts go into both. The question we are answering: does the output compile? And does it actually do what we ask? That's it. Let's start reading. Okay, reading time. 4 contracts, roughly 15 minutes each. For each one, we will do the same 3 things. Talk about the idea, look at the picture of how it all fits together, then walk through the actual code. Let's start with the smallest one, calculator. First contract, calculator. It's the size of a short email, about 20 lines, and all it does is arithmetic. 4 of the circuits are exactly what you would expect: add 2 numbers, subtract, multiply, square. Those are easy. But the 5th circuit, divide, is where this contract earns its place in the docs. Here's the puzzle. Inside a zero-knowledge circuit, division is really expensive to prove. So instead of doing the division inside the contract, calculator does something clever. It asks your local machine to do the math, and the contract just double check that the answer is right. We will see exactly how this works in a minute. For now, just remember, you're about to see the single most important pattern in Midnight. Here's the whole contract as a diagram. It fits on one screen. On the left, a user. They call one of the 5 circuits. The top box holds the 4 easy circuits: add, subtract, multiply, square. Each one just computes the answer and write it to the single storage cell on the right, labeled result. The interesting one is at the bottom, divide. It doesn't compute the answer itself. Instead, it reaches out to what's called the witness. That's the little dash box you see fitting in. And the witness returns both the question and the reminder. Then the circuit runs a quick math check. Is the reminder smaller than the divisor? And does question times divisor plus reminder equal to the original number? If both, yes, we're good. Otherwise, transaction rejected. On the state cell, 5 circuits, 1 witness. That's the entire contract. Let's look at the code. Here's the top of the file. Let's read it together. Line 1, the pragma. All that says is this file is written for Compact version 22. Every Compact file starts like this. Line 3, export ledger result. Here's our one and only storage cell. It's a 16-bit unsigned integer, which is a fancy way of saying can hold any whole number from 0 to about 65,000. Export just means this is part of the public interface. Then the add circuit takes 2 16-bit inputs. That little sign after the parentheses is the return type, empty tuple, meaning this circuit doesn't return anything. Inside, we do num1 plus num2. Then we cast with a as uint16 to make sure the sum fits in 16 bits. And when we wrap the whole thing in disclose, remember that word. It's how we say publish this value to the public ledger. Subtract, multiply, and square are exactly the same shape with the different operators. Once you have seen one, you have seen them all. Here's the clever trick. Imagine you want to divide 17 by 3. Inside a zero-knowledge circuit, long division is genuinely expensive to prove. So this contract does something sneaky. It says, hey user, you do the division on your own computer. Just tell me the answer. That's what the witness is. Look at line 1. Witness deep mod with a signature but no body. We are saying there's a function called deep mod somewhere in the user TypeScript code. We don't know how it works. Just give us the question and reminder when we ask. Now look at the divide circuit. Your local code does the math. In our example, question 5, reminder 2. The circuit grabs both values. Then comes the bouncer line, assert, which checks 2 things. The reminder has to be smaller than the divisor, and question times divisor plus reminder has to equal the original number. 5 times 3 is 15, plus 2 is 17. Matches, pass. If you like about that question, say you said 6 instead of 5, the math wouldn't add up and the transaction would be rejected. 2 quick details. See how divide doesn't have export in front. That just means it's private helper. Other circuits in this contract can call it, but outside users can't. And here's the big lesson. You will see this pattern absolutely everywhere in Midnight. Hard math on your laptop, cheap check on chain. Second contract, token transfers. This one is a tour because Midnight actually has two different token systems, and this contract shows you how to work with both. Here's the mental model. Imagine two axes. One axis is privacy. On one end, you have unshielded tokens. Balances are public. Anyone can see who holds what. Exactly like a normal bank account, or like ERC20 tokens on Ethereum. On the other end, you have shielded tokens. Balances live in your wallet as encrypted coin notes. Think cash inside a sealed envelope. Nobody can see the amount. The second axis is the token kind. Your contract can mint custom tokens, like a company creating its own loyalty points. Or it can work with Night, which is Midnight built-in native token. Quick note on Night. It's also what the network uses to generate dust, the token you actually pay transaction fees in. Think Night as the reserve currency, dust as the cash for fees. Mix and match those two axes and you get 4 combinations. This one contract shows 9 different circuits across that grid. It's a little overwhelming on first read, so we will take it piece by piece. Here's the grid, visualized. Privacy mode on the vertical axis, token kind on the horizontal. Top left box, unshielded custom tokens, has 3 circuits, mint and receive, send to user, receive tokens. These are for when you're creating your own token and everyone's balance is public. Top right box, unshielded 9 tokens, has 2 circuits, for receiving and sending Night. Think of Night as Ethereum or Sol, the native currency of the network. Bottom left box, shielded custom tokens, has 4 circuits. This is where you would build a private payment system. Mint to the contract, send to a user, receive, or mint and send in one atomic step. Bottom right box is empty. Shielded Night isn't in this example. Don't worry about that for now. 9 circuits total. We're going to read just enough of them to get the shape of how these work. Before the code, a quick warning. This contract uses a lot of Midnight specific type names. Let me just name them once so they are not scary when you see them. First surprise, this contract has no ledger declarations, no storage at all. That's because token balances don't live in individual contracts. They live in Midnight's built-in coin system. This contract is basically a thin wrapper that calls into that system. Types to recognize: user address and contract address. Pretty self-explanatory. Swap coin public key. That's a user shielded token identity. Shielded coin info. That's a fresh coin node. Qualified shielded coin info. That's a coin node that's been placed in the spendable coin tree and is ready to spend. And shielded send results. That's the receipt you get back from a shielded send. One pattern you will see constantly, left and right. When a function takes an address, it wraps it in either left or right of 2 type names. That's how Compact tells, is this a contract address or a user address? Left and right are labels for the 2 branches. And 3 helpers. Kernel self gives you the current contract address. Path turns a short string into a 32-byte domain separator. And token type derives a token color from its domain and minter. Let's read one. Mint and receive. The job: create some tokens and have the contract itself hold them. Notice the import at the top. Import compact standard library. That's where all the token primitives live. You will see this import on basically every non-trivial contract. First line inside the circuit, mint and shielded token, which is a built-in. 3 arguments, the name tag, the amount, and the recipient. We build the name tag in line by calling pad32 simple receive. Padding the string simple receive to exactly 32 bytes, that string is this token unique identifier. The recipient is kernel self. Send it to the contract. Wrap in left, because the left branch of this particular union means contract. The built-in hands back the token caller, a 32-byte identifier, and the circuit returns that to the caller. Everything goes through disclose because remember, unshielded tokens are public by design. All right, one circuit down. Rest are variation of this theme. 2 more circuits, quickly. Send to user. Contract sends tokens out to a user. First, it rederives the token caller using token type. Then, send unshielded with 3 args, caller, amount, recipient. Notice the recipient is wrapped in right, this time, not left. Same union, opposite branch. This means user address. And receive night tokens. Very short. It just calls receive unshielded with default byte 32 as the caller. That default value is Midnight way of saying this is a native token, night. No domain separator needed because night is built in. The other 2 circuits is in this contract, receive tokens and sending night tokens to user, are mirror images of this. If you have followed this, you've got them all. Now, shielded. Same shape on the surface, but underneath it's doing something radically different. Look at the input. The first argument is called input, and it's a qualified shielded coin info. That is not a balance. It's not a number. It's an actual coin note, a little encrypted bundle of money from the sender's wallet, like a specific $10 bill, not just $10. The return time is shielded send result, and this is where the magic lives. That structure holds a zero knowledge proof of the spend plus an encrypted ciphertext that the recipient's wallet will decrypt later. To anyone watching the blockchain, the only thing visible is a shielded transfer happened. No amount, no sender, no recipient, just a valid proof. That's privacy-preserving cache, implemented in 60 lines of compact. Last circuit, mint and send shielded. Mints new shielded tokens and sends them to a user, all in one atomic operation. 3 steps. Step 1, mint shielded token, creates a brand new coin node, sent to the contract itself. Step 2, convert that fresh node into a qualified shielded coin info by building the struct manually. And we set empty index to 0 because the coin is fresh and hasn't been added to an expendable coin tree yet. Step 3, send shielded forwards that qualified coin to the real recipient. Big takeaways across this whole contract. Pick the right token model on purpose. Unshielded when you need public auditing, a DAO treasury, a stablecoin reserve. Shielded when privacy matters, salaries, private payments. Night for pay network fees, custom tokens for your app. 9 circuits, but really only 4 patterns repeated. Okay, 2 contracts down, 2 to go. Let's make a brief summary. Keywords you can now read on site. Pragma, import, ledger, circuit, witness, disclose, assert, and the type cast with us. Patterns you have seen, the witness plus assert trick for doing expensive math of chain, and the two token models with the rule of picking one on purpose. What's coming next? Private guest list is going to throw a bunch of new primitives at you. Sets, sealed cells, enums, constructors, cryptographic commitments, per the app keys. After that, election pulls all of it together with maps, counters, and multi-phase state machines. If you have followed up to this point, you are in great shape. Let's keep going. Okay, contract 3, private guest list, about 80 lines. This is where real privacy engineering kicks in. Picture this scenario. You're throwing a private party. You want a guest list, but you don't want a list of names posted on a public wall where everyone can read it. Guests should be hidden during the lead-up and only revealed when they actually show up at the door. That's exactly what this contract does. Organizers add guests to the list, but all the guests stored on-chain is a cryptographic hash. You literally cannot tell whose name is behind each hash. When a guest arrives at the party, the organizer checks them in, and that's the moment their identity becomes public. The contract has a simple two-state bridge. Not ready while you are setting up, ready once the party is live and check-in are accepted. And there's a hard cap on guests, 99 max, making a deploy time and impossible to change. One more nice touch. Organizers are identified by per app derived keys, which means nobody can follow a single person across different DApps. Cross-app tracking just doesn't work in Midnight. Let's look at the picture. On the left, the organizer role. Organizers can call three functions: add another organizer, add a guest, and check in a guest. In the middle, the state machine. Two states, not ready for setup, ready for the party itself. You can flip to ready two ways, either automatically when the guest list fills up, or manually via a function called chain start party. On the right, three sets of data stored on the chain. The first is organizers, the people with admin rights. The second is hash party goers, the guest commitments. Think of those as sealed envelopes with cryptographic fingerprints on the outside. You can tell there's an envelope there, but you can't see inside. The third is check in party. This starts empty and fills up as guests actually show up, because that's when we crack open the envelopes. And off to the side, our seal max list size, set to 99 at deploy, frozen forever. Let's look at the actual storage declaration. 6 things in total. First, the enum, party states, with 2 possible values, not ready and ready. That's our phase tracker. Then 5 ledger cells, organizers, a set of 32-byte hashes. Remember what the set is. No duplicates. Membership test is quick. These hashes are the derived per app keys of our admins, not raw identities. Hash party goers, another set of hashes. These are the guest commitments, the envelopes. Check in party, a set that fills in over time. When someone actually arrives, the real plain text identity gets dropped in here. Party states, one cell holding the current phase, start at not ready. And finally, seal ledger max list size, an 8-bit unsigned integer, so it can hold any number from 0 to 255. Because it's sealed, the constructor writes it exactly once, and then it's locked forever. 2 witnesses. Remember, That's private data living on the user's device. Local escape returns the caller 32-byte secret key, their identity essentially, lives only on their computer. And local start party returns the caller's opinion about whether the party should start. We will see where that gets used. Now, the constructor. This runs once, when the contract is deployed. One line does a lot of work. It takes the deployer's local secret key, derives their per-app public key using the public key helper, which we will see at the bottom of the file, and inserts that derived key into the organizer set. Whoever deploys is automatically the first admin. Then set party state to not ready and write max list size to 99. Because max list size is 0, this is one and only assignment. After this constructor finishes, it's frozen for the life of the contract. First, real circuit, add organizer. Add another admin to the organizer set. Interesting choice. The argument is the secret key of the new organizer, not their public key. A little unusual. Here's why. We need to derive the new person's per-app public key the same way we derive our own. And that derivation uses their secret. Inside the circuit, 3 checks. Think of them as the bouncer checking 3 things at the door. 1. The caller must already be an organizer. 2. The new person must not already be in the list. 3. The party must not have started yet. Only if all 3 pass do we insert the new organizer. Here's the detail I want to highlight. Every identity stored on chain is a derived per-app key, never a raw key. That means nobody can look at these contracts later, see an organizer hash, and connect it to the same person in some other Midnight app. Privacy across apps is built in by default. Second circuit, add participant. An organizer is adding someone to the guest list. 4 checks at the door. Caller is an organizer, check. Party hasn't started, check. List isn't full yet, check. Then we build the commitment, the sealed envelope for this guest, using a helper called commitWithSk. What the helper does is hash the participant public key together with the organizer secret key. So the stored value is scrambled in a way that nobody but this specific organizer can recreate. Fourth check. This exact commitment isn't already in the set. Then and only then we insert it. There's also a little bit at the bottom I'm skipping on the slide for space. It says, if we just added the 99th guest, the list is now full. So let's automatically flip the state to ready. The contract double check this is what the organizer actually wants, using that local start party witness we declared earlier, and then flips the switch. One nuance worth flagging, because commitments are hashed with the organizer's secret. It's the same organizer who added a guest who needs to check them in. A slightly opinionated design choice. This is the reveal step. A guest shows up at the door. Organizers check them in. The organizer passes the guest plain text public key, their real identity. The circuit recomputes the commitment using that identity and the organizer secret, the exact same way we did at registration. If that recomputed commitment is in our hash party goers set, the guest was legitimately registered. Proof it matches, and only then do we disclose the guest's real identity into check in party. Notice how the privacy property flips at exactly these moments. Before checking, only a scrambled hash is on chain. Observers cannot tell who's on the list. After checking, the plaintext identity is right there in the check in party set. The guest is fully public once they actually arrive. That's the clean privacy boundary the whole contract is built around. Two helpers to close out the contract. Chain start party. It's an escape hatch for organizers. Maybe the party starts before the list fills up. This function lets an organizer manually flip the state to ready. A standard access checks. Then it calls the local start party witness to confirm the organizer really wants to do this, and flips the switch. And public key. This is the per app identity derivation we have been using all along. Look at what it does. Takes a secret key, hashes it together with the literal text guest list pk, returns the 32-byte results. Here's the trick of the century. Every midnight contract uses its own literal text label. Election uses election pk, guest list uses guest list pk. Same person, secret key produces completely different identifiers in different contracts. And there's no computer in the world that can figure out that connection. Cross-app tracking is not just difficult in Midnight, it's cryptographically impossible. That's pretty cool. Big takeaways: commit, assert, disclose. Hide it with a commitment. Check it with an assertion. Reveal it on purpose. That three-step dance is the recipe for private membership on a public chain. Add per app key derivation on top, and you get cross-app and leakability for free. You just added a bunch of tools to your belt: enums, sets, seal ledger cells, constructors, persistentHash. You're ready for the final boss. Contract 4. Election. About 130 lines. And this is our boss level. Every compact feature show up somewhere in this file. A scenario: an anonymous two-candidate vote. Could be a DAO choosing between proposals, a neighborhood vote, whatever. 4 stages. First, registration. Voters sign themselves up. Second, commit. Once voting opens, each voter drops a sealed envelope into a box. Their vote is inside, but nobody can see it. Third, reveal. Voting closes. Voters open their own envelopes to reveal their actual choice. Fourth, tally. The organizer declares a winner. 3 properties make this contract interesting. Privacy. During voting, only the sealed envelopes are on chain. Integrity. At reveal time, you cannot change your mind. The circuit verifies your reveal matches the envelope you drop. Anti-tracking. Voters are identified by per app keys, so nobody can follow a voter into some other contract and figure out how they voted. 4 stages laid out left to right. Stage 1. Register. Anyone who wants to vote calls register to vote. Voting state is closed. Then the organizer calls open voting and the state flips to open. Stage 2. Commit. Voters call commit votes. They drop their sealed envelopes. Organizers calls closing voting. State flips back to close. Stage 3. Reveal. Voters call reveal vote. The counters tick up. Stage 4. Tally. Organizers call check winner, and the winner gets written to a public set. The contract only has 2 name states: close and open. Close gets reused for the registration phase and the reveal phase. It's a little confusing at first, but the contract figures out which phase it's really in by looking at other data, like whether there are any commits yet. Fine in practice, just unusual on first read. Two little enums. Voting state has two values, close and open. That's our gate between phases. Vote choice has three values, bad, worse, and tie. Yes, those are the names. The dogs are having a bit of fun. Bad means candidate 0 won my vote. Worse means candidate 1 won my vote. Tie is never submitted by a voter. It's only ever said by the contract itself at the end, if the counts happen to be equal. 10 storage cells. Let me group them so it doesn't feel overwhelming. 3 CL cells, all log a deploy time. Organizer is the public key of whoever deployed the contract. Only they can run the admin functions. Candidate 0 and candidate 1 hold the two candidate names. Nobody can swap candidates mid-election. Then the mutable stuff. Voting states, the phase switch. Hash vote map is the key to the whole contract. A map where each key is a voter's ID and the value is the sealed envelope holding their vote. Registered voters is a set, the list of people allowed to vote. 3 counters. Total vote count goes up every time a commit lands. Candidate 0 vote counter and candidate 1 vote counter are the actual tallies. They only go up during the reveal phase. And winner, a vote choice cell that's empty until the organizers declares the result. 2 witnesses. Local get vote returns the voter's pick, which lives only in their local app, never on chain. Local SK returns their 32-byte secret key. The constructor takes the two candidate names as arguments. It writes the deployer's public key into organizer, writes the two candidates' name into their sealed cells, using disclose because those cells are public. Sets the state to close, so registration can begin. Done. After the constructor finishes, those 3 sealed cells are permanently frozen. Voters sign themselves up. No arguments. The voter's identity comes straight from their own secret via the local SK witness. Pull the secret. Derive the per-app public key. Check you are not already registered. Check voting hasn't started yet. Insert. Same trick as before. Because we use per-app keys, the same voter is totally unlinkable across different Midnight apps, but perfectly stable within this contract. Exactly what we need. Short and sweet. Organizer flips the state from close to open. 3 quick checks. You are the organizer. Owner check. The state is still closed. Can't flip twice. At least one voter has registered. No point opening with nobody. Then the assignments. Voting is live. One conceptual bit worth pausing on. Look at the owner check. It uses one public key. The voter's raw public key, not the per app derived one. Meanwhile, voters use getDappPublicKey. Why the asymmetry? Because the organizer identity is supposed to be publicly known. They deploy the contract. They're the official admins. Voters, by contrast, need to stay anonymous inside the contract and unlinkable across the apps. Different people, different privacy goals, different keys. It's a deliberate asymmetry. Voters drop their sealed envelopes. Let me walk through it. A state must be open. Pull your secret. Derive your per-app key. Check. You're registered. Check. You haven't already voted. No double voting. Pull your private vote from the local get vote witness. Make sure it's a valid choice, but or worse, not tie. Then the clever bit, build the commitment. We cast the enum to a byte string, and then we hash it together with your secret key using commitWithSk. By combine it with your secret, because the vote is just 3 possible values. If someone tried to crack it, they could just try all 3, but adding your unique secret makes the hash effectively uncrackable. Drop the commitment in the map. Bump the counter. Your vote is sealed and on-chain, and nobody can tell what it is. Here's the best part. Voting has closed. Time for you to open your sealed envelope. Pull your secret. Derive your voter ID. Confirm you did actually commit earlier. Pull your vote from the witness again. Range check that it's bad or worse. Reveal the exact same hash. Both combined with your secret. Now look up what you stored during commit. And then this single line does all the work. Assert that your stored commitment equals the new hash. Here's the magic. If you try to reveal different vote than you committed, maybe you had second thoughts. The new hash won't match the stored hash. The assertion fails. The transaction reverts. You cannot change your mind. The contract forces honesty. If the hashes match, your vote is honest. The circuit discloses and bumps the right counter. Candidate 0 gets a vote, or candidate 1 gets a vote. 2. Admin circuits. Close voting. Organizer confirms voting is done. Check you are the owner. Check there's at least one commit. No point closing an empty vote. Flip the state back to close. From this moment on, voters can reveal. Check winner. Declare the results. Owner check. State check. Then a simple 3-way comparison. If candidate 0 has more votes, winner is bad, which, remember, is just the label for candidate 0. If candidate 1 has more, winner is worse. If they're equal, winner is tie. One public cell, one final answer. Everyone can read it. The 2 little helpers at the bottom of the file. commitWithSk. Hash the vote together with the secret key as a 2-element vector. Returns 32 bytes. That's how we seal envelopes. getDappPublicKey. Same persistent hash primitive, but with a different label. Election PK this time. Same trick we saw in guest list, which used guest list PK. Different label, different per app identity. Same person, totally different hash in 2 different contracts. You keep using this pattern because it works. Zoom out. Every major compact feature lives somewhere in election. Enums, sealed cells, maps, sets, counters, constructors, witnesses, asserts, disclose, persistent hash, owner checks, per app keys. And the big structural lesson is this. State gates plus commit reveal plus per app identity is a template. Swap out the witness and the tally logic, keep the same bones, and you've got a sealed bit action, a time reveal, an exam with late grading, whatever. Whole family of contracts, all variation of election. One bonus before we leave section 2. 4 mistakes I see almost everyone make when they first write compact. Learn this now, save yourself hours later. Number 1, forgetting disclose. When you write a private value into a public ledger cell without wrapping it in disclose, the compiler catches it as a type error. Number 2, putting expensive math directly inside the circuit. Division, big loops, sorting, proof generation balloons, builds get slow, users wait. The idiomatic answer is always the calculator pattern. Move the math into a witness, then verify the answer cheaply with assert. Number 3, using raw public keys for user identity. Same user, multiple DApps. If you use ownPublicKey everywhere, all those activities become correlatable. Exactly what Midnight is trying to prevent. Use per app derived keys whenever you need user identity inside a contract. Unless, like the election organizers, you want the identity to be public. Number 4, forgetting access control asserts on the state mutators. Every circuit that changes the ledger should have an assert at the top checking who's allowed to call it. No guard means anyone can call it, which means your contract is broken. Now, let's put AI to work. Okay, we can read compact now. Let's see if AI can write it for us. 2 tools, live demos. 3 ground rules, so the comparison is actually fair. Rule 1, intent first prompt. I'm going to describe each contract the way you would describe it to a human developer. What it should do, not what variables to create. No function names, no type names, just the product brief. That way, we are testing whether the AI understands compact, not just whether it can follow a recipe. Rule 2, same prompt into both tools, word for word. Rule 3, first output only, no follow-ups. Any difference we see has to come from the tool itself. First up, Web3 Fast. Web3 Fast is a website. You go to the URL, you type a description of a contract. It spits out compact. That's the whole product. Free, no account, no install, which is really its superpower. Anyone with a browser can start building on Midnight in 30 seconds. It's an official ecosystem partner listed in the awesome DApp collection. What is the catch? It is a shared service, so the quality depends on whichever AI model the operator has plugged in and how well tuned their prompt setup is. Fine for learning, a little less predictable for production. Let's try it. Quick tour. The whole UI is 3 panels. On the left, you type your request. In the middle, the generator compact code appears when you hit submit. On the right, copy or download the result. That's it. No tabs, no wizards. Let's generate our first contract. Okay, let's start with the first example, the calculator, using Web3 Fast. In this slide, you can see a brief summary of what we are going to do. Okay, let's switch to the terminal. Let's continue with the second example, token transfers, using Web3 Fast. In this slide, you can see a brief summary of what we are going to do. Okay, let's switch to the terminal. Okay, let's continue with the third example, private guest list using Web3 Fast. In this slide, you can see a brief summary of what we are going to do. Okay, let's switch to the terminal. Okay, let's continue with the fourth example, election, using Web3 Fast. In this slide, you can see a brief summary of what we are going to do. Okay, let's switch to the terminal. Quick intro. Code is an Anthropic official command line interface. It's a coding assistant that lives in your terminal and is powered by Cloud. It requires a paid subscription. The DApp-scoped plugin builds on 4 Midnight specific skills. Midnight docs can fetch live documentation pages. Midnight examples pulls reference DApp architectures. Midnight starter holds project scaffolding templates. And Midnight docs repos has deep technical reference for the SDK internals. Every time you ask Cloud to write compact, it can reach for exactly the right context. That's the plugin whole value proposition. It gives the assistant a curated, up-to-date Midnight knowledge based on demand. 5 practical differences. Install URL versus CLI plus plugin. Cost free versus subscription. Interaction 1 prompt, 1 answer versus conversational and iterative. Context whatever the hosted model was trained on versus live docs pull fresh. Output just the contract file versus potentially a whole project, test, CLI, front end. For this comparison, we are only scoring first outputs to keep it fair. The conversational advantages, interaction, project, scaffolding, are real, but they would leak into the scorecard unfairly if we counted them today. Okay, now let's start with a quick tour through the Cloud code plus the DApp-scoped plugin. Okay, let's do again the first example, the calculator, but this time using the Cloud code with the DApp-scoped plugin. In this slide, you can see a brief summary of what we're going to do. Okay, let's switch to the terminal. Let's continue with the second example, token transfer, using Cloud Code and the Labs plugin. In this slide, you can see a brief summary of what we're going to do. Okay, let's switch to the terminal. Okay, let's continue with the third example, guest lists, using Cloud Code and the Ada Labs plugin. In this slide, you can see a brief summary of what we're going to do. Okay, let's switch to the terminal. Okay, let's continue to the last example, election, using Cloud Code and the Ada Labs plugin. In this slide, you can see a brief summary of what we're going to do. Okay, let's switch to the terminal. We have watched both tools generate all 4 contracts. Now, let's be honest about what came out. For each contract, we hand out a report card, grades per criterion, an overall mark, and 1 sentence from the instructor. Web3 Fast and Cloud plus Ada Labs side by side, no hand waving. Pulling it together, Cloud Code was better across every contract, and the report card made that objective. 2 reasons. First, the underlying LLM. Claude is a stronger reasoning model than whatever hosted model Web3 Fast operator has wired in today, and that show up on the harder prompts, guest list, and election. Second, the Ada Labs plugin. Every time Claude writes compact, it can pull from 4 skills: Midnight Docs, Midnight Examples, Midnight Starter, Midnight Docs repos. These skills are curated and updated with the latest Midnight platform changes. So Claude isn't relying on training data from a year ago, it's reading this week's Midnight. That's the capability side, but there's a cost. You pay for a Claude subscription. You install the Ada Labs plugin from the Cloud Marketplace. You set up the CLI locally. None of that is free. None of it is instant. Web3 Fast answer is still valid. 0 install. Browser only. No account required. For a learner opening Midnight for the first time, Web3 Fast is the right door. For shipping production DApp-scoped, you want the paywall route. Let's head to section 5 and turn that into a pick your path decision. We know Cloud Code was better, and we know what that cost you. The only question left is what you do with it. Both tools have a place. The right one depends on who you are today, not on an abstract winner. Here's my rule of thumb. Are you a learner on no budget, just exploring? Start with Web3 Fast. The output is more than good enough for understanding compact by example. And the 0 barrier thing is a massive win. No install, no account, browser tab only. Are you a professional building an actual DApp that needs to ship? Cloud Code plus Ada Labs is a worth the subscription. The interaction, the project scaffolding, the ability to generate tests and CLI and front end alongside the contract, that saves you real hours. And for a lot of people, the sweet spot is using both. Draft your idea in Web3 Fast. Copy the result into Cloud Code. Let Cloud turn the draft into a full project. 2 tools, 2 moments, each doing what it's best at. Links to keep. The 4 reference contracts we studied are all at docs.midnight.network. The compact playground, which we use to compile the AI output, is playground midnight network. We cover it in depth in episode 2. Web3 Fast is at midnight Web3 Fast dev. The AdaLab plugin ships through the Cloud Code Marketplace. And the Awesome the Apps repo has everything else the Midnight community has built. Bookmark all 5. They will carry you through the rest of the series. See you in next episode.